It's the last presentation of these 2 fantastic days. Hopefully you can stay awake for another presentation. And like Chris just mentioned, there's another workshop after this on basically what we're talking about here. And Olga and me are doing this together, so we've got sort of a few slides each that we're talking about. But it's also a study that quite a few other people have been involved with, that we've been doing at the Swedish School of Sport and Health Sciences. And just as a little bit of background, there's quite a tradition in Sweden for pretty innovative methods that are often quite invasive. There's, at the Swedish School of Sport and Health Sciences, it's the muscle biopsies sort of originated there in the 60s and then sort of went to America and have been used in a few other countries now. But it really is a center of where the muscle biopsies with P. or Åstrand and others, that they started that off. I'm pretty sure most of you have seen some of my stuff on the bone pins, the intracortical pins that we've been drilling into people's feet and legs. And then we've also got this intramuscular EMG. And it's not because we've got easier ethics, which a lot of people often think. We've got really good ethics in Sweden. But they, like you're supposed to with ethical approval, they weigh risks against benefits, and the benefits of these studies outweigh the risks. And we've been showing this with all of these stuff that we've been doing. So just as a bit of background, and GIH really has been one of the centers in the world that have started off this intramuscular EMG for the last 30, 40 years. So some of the stuff that's been done, this was Eva Andersson from GIH, who did a PhD thesis using intramuscular EMG. Unfortunately, she's got no photos in her thesis of where the electrodes were inserted, but she was looking at the deep lower back muscles. And I'm not sure, but I think she's one of the only ones that's actually looked at the psoas muscle, which is really deep, which is pretty impressive. And I mean, it's quite the actual study and the questions that she was looking at are quite simple. It's just some functional movements, just to explain on a basic research level what the muscles there are doing, and especially the psoas. I mean, it was pretty cool. And also, she had some work on this. Actually, we've been looking for a sartorius. We're thinking about the workshop later. We might be doing the sartorius. Yeah, and just another picture from the article then that she published in '96, which was part of her thesis, looking again at the same muscles with the psoas. And as you can imagine, you need different length pins or needles to put the electrodes into all of these muscles. We've sort of had a renaissance of this method in the last 10 years. Had a PhD student from Brazil, Julio Cesar, and he looked at at 8 different muscles in the thigh, so 4 quadriceps, 4 hamstrings, and doing some functional movements, mainly cycling. And here we'll just show a little bit of a video. You'll see this later in the workshop as well, because we've got the ultrasound there. But what I'd like to just point your attention to, from here you will see a needle coming in. And this is actually the vastus lateralis and the vastus intermedius down here. And as you can imagine, I mean, the advantage with intramuscular electrodes is that you can get muscles that aren't on the surface. And the vastus intermedius, you're never going to get with surface electrodes because it's pretty deep. And then it feels really nice when the needle goes through the vastus lateralis, and then there's another big fascia here that it has to sort of get through, and then it gets into the intermedius. But the last bit, no, wait, I have to press that first. We thought of putting some music on here, but couldn't think of the right song. Okay, you can see the needle coming in there. And I mean, even within the muscle, sometimes it's quite hard to get through you can see a contraction coming up here somewhere, where it obviously hurt a bit. And unfortunately, it stops here somewhere. But so we had in the vastus medialis, the lateralis, the rectus femoris, and the intermedius. And on the right-hand side, you can see there's a lot of logistics that has to go into this, because the muscles are quite long. So there's quite a lot of places that you can actually put the electrodes into them. But we also need to have an experimental setup where you have to have all the wires taped. The person has to be able to move. And so we tried to find a level where we could have all of the muscles roughly on the same level across here, so that we could have all the equipment at the same place, which we can see on the next photo. So we've got, I mean, it's quite a lot of stuff that you have to sort of tape onto the person. And you can see, I hope you can see, the electrodes coming out, the fine wires coming out of all the... We didn't use, what you'll see this afternoon is 2 fine wires in each needle. We had 1 in each needle, and so that we could stick them in a bit more often. So we had twice for each muscle, so that they could be a bit further apart. Because otherwise there's a risk that there's a short circuit between the fine wires. So what's that? 8 muscles times 16 holes in there. And that's then what the subjects look like. So like I said, with that many muscles, it's quite an issue to get it all well set up. This is a video. So we did quite a few things. That what Julio ended up publishing was actually on cycling. But this is just a concentric on an isokinetic dynamometer. Concentric. I didn't realize this. That's one shaky subject. Well, that was cool. I didn't realize there was sound on that. Eva's always into... Wow. It didn't do this when I was looking at it last time. That's someone running downhill. And we actually, I mean, people often say, can you do this in very dynamic movements? We ended up running at 20 kilometers an hour, the fastest guys on the treadmill. The data was not always perfect, but we wanted to try it at really fast running as well. But like I said, the main study that Julio did was the cycling, looking at the coordination of the quadriceps and hamstrings during cycling. And just an example of the results that he got. You've got the 8 muscles here, the 4 hamstrings, 4 quadriceps, and 3 different intensities, which are the 3 different colors or shades of gray of the muscles during the complete crank cycle, so from 0 to 360 degrees. And I mean, this is basic research stuff as well, because people have been doing it with surface electrodes, but by having it intramuscular, we could really see which muscle was doing exactly what. And sort of basically the same thing, just illustrated in a different way there. So, really valuable information just to get from the thigh muscles. We had 2 PhD students that were actually PhD students in Jyväskylä in Finland, Andras and Anna Maria, who are actually married, which has got absolutely nothing to do with this. And what Andras was looking at was the hamstring muscles, and not just looking at one position, because one of the criticisms of intramuscular EMG is that it's a very, very localized area that you're looking at, like even single muscle units, motor units. Whereas with surface EMG, you're actually looking at a bigger area, even though you might get crosstalk and stuff. So what he looked at was not only having in one set of electrodes in each muscle, but putting 2 or 3. I think he had 3 in each, distal, middle, and proximal, so just to make a few more holes. And he also had these, what are they called? Where it's not just a single set of electrodes, but across the whole muscle, to compare different areas of the same muscle during hamstring activity. And once again, I mean, you can see on the right-hand side, it's not easy getting that many electrodes to work at the same time. But that's not what we're talking about today. So that was a bit of background, just a couple of the studies that we've been doing. But what I wanted to look at today was what's mainly Anna Maria's study. And that was looking at the plantar flexors of the foot during walking at different speeds and wearing different barefoot shod and in flip-flops and a few other conditions. The reason for this was I was an opponent for a PhD thesis in Jyväskylä, and the PhD student had based a lot of his thesis on surface electrodes on the flexor hallucis longus. And one of my main criticisms was, what on earth are you measuring? Because I really didn't believe that. Great thesis. I mean, everything was really good, and he obviously passed and everything. But I didn't trust the data from a surface he had it medially behind the medial malleolus. And of course, that's where the flexor hallucis longus is, but there's lots of other things there as well. So how did he know that was that? And so they sort of challenged us and said, okay, we'll come over to you guys and we'll do intramuscular. Let's see what we're actually measuring. So that was a background to this, but then there's lots of other questions that sort of came up, as they always do, to also measure. One of the cool things with being an opponent in Uvascular is before you go into the hall, everyone's quite dressed up in their coats and stuff. And then this was when Pavel Kormi was still there. And he takes you into a little room and you get a little whiskey before you go in and you go and be your opponent. It's fantastic. I can highly recommend it. I'll just go past that one. Yeah, so we're looking at the triceps surae, medial gastrocnemius, lateral gastrocnemius, and soleus, but also the flexor hallucis longus, which isn't on that picture. It's on that picture. And as you can see, there's that's why I'm a bit doubtful, because there's other muscles there. There's the flexor digitorum longus mainly, and the tibialis posterior, which I thought would be complicating what we're actually measuring. It's actually quite a big muscle. If you look at it on ultrasound, and maybe we can do that later, we can have a quick look at the FHL as well. It's a big muscle, which you don't really think of. But I mean, the hallux is obviously very important when you're walking, and it's a very strong joint. So I mean, it's a big muscle that's controlling that. And it contributes a lot to the load transmission during locomotion. And it's actually, I mean, there's a lot of, I'm not sure how they did this, but there's studies showing the high forces that can be produced by the FHL. So the aim was to look at the fine wire activity of 4 ankle plantar flexors at different speeds and wearing different footwear. This is doing a swap over here.
So, yes. So as Toni already introduced, so one of the PhD students in Uvascular, so Anna Maria, was doing a study in our lab. And this particular study was focused on comparing surface and fine wire EMG activity of lower leg muscles, also different walking speeds. And so we did measurements with both surface and intramuscular EMG, and to compare. And for the intramuscular EMG electrodes, to insert them, we used the high-resolution B-mode Doppler ultrasonography, and we used Teflon-coated 7-stranded silver wires. And when we inserted 2 per muscle, and with a distance of approximately 5 millimeters apart, and the diameter was 0.25 millimeters. And so here is shown 4 muscles that we had the EMG electrodes on, and the surface first, and you can see the lines here. So that was the placement of the surface electrodes. And for soleus, medial and lateral gastrocnemius, so the intramuscular EMG electrodes were placed underneath the surface, but for flexor hallucis longus, it was approximately 5 to 10 centimeters proximal to the surface EMG. So it's like here. And also lateral, on the lateral side of the shank. And it depends on the thickness of the muscle belly and also vascularization. Did I forget anything? So, and this study, so yeah, introducing a little bit of methods as well in the protocol. So it started with the familiarization session, during which we did some isometric force contractions on the dynamometer with the ankle joint flex at 90 degrees. And also the participants were introduced to the study protocol, and during this session we made some preparations for the electrode placements, for example surface, and also where approximately the intramuscular EMG would be inserted. And also they did some walking in the lab, just to be comfortable with the protocol. And after approximately after 1 or 3 days, there was another session, the actual data collection session. And so, as I mentioned before, intramuscular and surface EMG and 4 muscles, and we did measurements on the right leg. And for this particular study, we measured 10 participants. And the session started with a warm-up on the dynamometer with a isometric contractions, plantar flexion and dorsiflexion. So we did 3 maximal isometric plantar flexion contractions, and also 3 maximal big toe flexion. So it's superimposed on ankle plantar flexion contractions. And this data from the dynamometer we were planning to use for the EMG normalization as a maximum voluntary isometric contraction. And it was 3 repetitions per movement. And this session followed by the walking tasks. So it's overground walking. So our walking distance we defined 7 meters, and in the middle was the force plate. But the actual walking started 3 meters before and after the actual measurement distance, to ensure or try to control that it was a walking steady speed. And to measure the speed, we had custom-made photocells that was placed before, at the beginning and in the end. And in this session, so it started with 5 walking trials, where the participants were instructed to walk with a self-selected speed, and the fastest and the slowest were excluded, and those remaining 3 were used and defined as a preferred speed. And then we also collected trials with a 30% slower walking and 30% faster walking, and also the maximum speed where the participants were instructed to walk as fast as possible. And they did the walking trials in the shoes, barefoot, and also flip-flops. And it was 3 or 5 trials each condition. So we collected data, or we used data that we collected with the force plates, and also we were measuring the pressure insoles or pressure distribution insoles to define the events of the heel strike and the two off, to define the stance phase. And for the trial where the participant actually was stepping on the force plate, we defined also the push-off phase where the ground reaction force was 0 Newton. And here are the example of the whole stance phase and the raw EMG activity from the intramuscular from all 4 muscles here. Yep.
So it is some of the results. This is the 3 different, or it's 4 different walking speeds. We had one slow that was a 30% slower than preferred, and one fast, which was 30% faster, and then the maximum. And what you can basically see, this is the intramuscular EMG only, not the surface, is that the 4 muscles over 100% stance phase, so it's normalized to stance phase. And you can see, I mean, the curves are pretty similar for all of them. Obviously, the activity increases when you're walking faster. And maybe the most interesting part is that the soleus and the medial gastrocnemius swapped over a bit from the slower to the faster walking. So at the slower, the medial gastrocnemius was the dominant muscle, whereas at faster, the soleus was actually more dominant. So just general basic research information on what the muscles were doing. Now we're into, where's Clint? There. Looking at the complete trial, and it's SPM, yes, statistic parametric mapping. Something that we've been doing for about 5 years, quite a lot, and a lot of people are starting to use it now. A bit complicated to understand first, but it's actually really, really useful, we find. So what we're looking at, maybe the most interesting, is blue is fine wire and yellow is the surface electrodes. And you can see the smoothed EMG curves on the top of for the 2 different methods, fine wire and surface. And what you can see on the bottom is the actual statistical analysis. And what it basically is, it's a repetitive, I'm very, very simplifying it here, repetitive t-tests across the whole whole trial. And there's the dotted red lines are significance. So if the curve showing the difference between the time series crosses the dotted red line, there's a significant difference just at that point. And this is only for the fast walking, because there weren't any significant differences for any of the others. But here you can see, for example, that the curve does go below the red line, which means that at exactly this point, there is a significant difference between surface and intramuscular. And you can see that as well on the soleus, and especially on the tibialis anterior on the right-hand side here. But the main question that you might remember from the opponent in uvascular part was whether the surface EMG of hallucis longus would be correct or representative of the intramuscular. And it basically was, with the exception of one little part here. So I was sort of proved wrong there. They did actually get pretty good with the surface electrodes on the medial side of the shank. Same thing here, looking at different footwear. You can see, once again, 4 muscles, not the tibialis anterior in this case. And all the different conditions here, all of them now shod, barefoot and flip-flops, all on the same curves. And in this case, we actually saw basically no significant differences. Once again, the dotted lines are the significance on this SPM, and the curves they just nudge the line once here on the lateral gastrocnemius, but basically between these shoe conditions, which we found surprising. We thought the flip-flop especially would have higher activity for the flexor hallucis longus due to the way that you have to walk with flip-flops so they don't fall off. We actually had quite big discussions here, how much difference it makes if you're used to it or not. And maybe they had too many Australians as subjects here. They wear flip-flops all the time. So basically, in shod walking, the muscle activity was higher. And one of the ideas or hypotheses there is that the shoes might actually impair the spring-like function of the leg. At the higher walking speed, the soleus and the flexor hallucis longus activity increased most, and slightly less in the 2 gastrocnemiae. And the activity strategies changed with speed. The flip-flops did increase the relative activity of FHL a little bit, as I showed, compared to barefoot, but maybe not as much as we were expecting. but maybe this would have a possibility as FHL training implications, and we might also see Achilles tendon problems due to the altered FHL force production and morphology. I'll finish there. Like Chris mentioned, we've got a workshop in a couple of minutes. I'm sure everyone's ready to get up and move around a little bit. It's Tanika that's in charge of it, and I'm just providing a muscle, so that's my job for the next 1.5 hours. Thanks for your attention. If there's any questions, you're welcome, or you can ask them at the workshop as well. Chris.